So we are now recording. Let's see if PowerPoint will come up from current slide. And we'll wait for the dark screen to go away. I don't know why this takes so long to load an empty screen, okay? Here it comes. And I'll get out of presenter view. And then we'll get back into both on the same slide page. There we go. All right, any questions from anything we've done up till now? All right. All right, of course. Let's note some things about matrix multiplication. Table Theorem 2.3, we listed several properties of matrix multiplication having to do with associative, if everything's sized properly, distributive, if everything's sized properly, okay? And, you know, but guess what? We didn't mention commutativity. So let's take matrix, well, let me get my pen. You know, yeah, I'm recording. Okay, I didn't see for a moment my
I know we've touched on
screen cap.
This, but I think we did it before they even started
Right.
talking about it.
Exactly. So here's matrix A, a very simple 2x2 matrix, 1, 3, 2, -1. And matrix B, which is 2, -1, 0, 2. And the question is, can we multiply those two? Yeah. AB would then be the product of those two. And can I just do it from here? Do I have to write them again next to each other? Okay. So what size will the product be? A 2x2. First entry there, or pick one of the entries.
It'd be, top left.
Yeah. So you would do?
It'd be 2.
Huh?
It'd be 2.
Okay.
It'd be 2 times 1 and 0 times 3.
Exactly.
Add them together.
Already ahead. Okay.
Well, 0.
The second, yeah, 0 made it. Okay.
I'll be lazy. Go
Second entry.
one right below it.
Which one you want to do next?
The one below the 2.
One below the 2, that would be the 2-1 entry.
Yeah,
So second row, first column, and that would be a 4. Okay, he is really lazy. Okay, next.
All right, so top right.
Top right, that would be first row, second column, that would be
-1 and 6, which is 5.
5. Okay, and
Last but not least, that would be -2, +2, 0. Right.
do that one more time.
-2. Oh, plus negative 2. I didn't see that. -4.
-4. Okay. All right. Now, the next one may be a little bit tougher. So what I'm going to do is rewrite A. 1, 3, 2, -1. And let's now do BA. Multiply B times A. It will also be a 2x2. And the first entry here will be?
Let's see, it'd be 2 times 1, which is 2, plus -2, which is 0.
Ah, that one is 0. Just ahead of his time. Okay. Next.
What way do you usually?
It doesn't matter to me. You just name it and claim it. Okay.
Okay. The one below that.
Okay, that would be the 2-1. So second row, first column, that would be
4, which is
4. Okay, good deal. And then I assume you'll do
second column, first entry.
Okay, first row, second column. Okay. What would that be?
That would be 2 times 3, which is 6, plus 1, which is 7.
7. Good deal. Next, last.
Alright, so 0 times 3, which is 0, plus -2.
-2. Perfect.
Plus
And what do you notice about these two?
Could
Yeah, one random entries happens to be the same. Yeah, they are not the same. AB and BA are definitely not equal to each other. Okay? Now, if A and B were not square matrices of the same size, then AB and BA would not even be the same size, okay? And in fact, there's a real good possibility, even if you could do one multiplication, the other one wouldn't even be defined. It just depends on the size. But if they're square matrices, and multiply them either way will give you matrices that are also square of the same size, then you don't expect them to be equal, even if you can do it, okay? However, this is jumping a little bit ahead, there are some that are commutative. Those are special, okay?
Probably the,
yes.
well, a zero matrix, obviously, probably
Right.
one. What else? The identity matrix.
Yes, for sure there.
There's probably more. But
Inverse matrices.
yeah, the inverse.
And the inverse matrices will do it. So those are all very special case matrices, okay?
That was a quick little example.
Yeah. So AB is, in general, not equal to BA. If it is, you have a special case on your hand. Now, do not conclude from example 4 that the matrix products are never equal. Sometimes they are, and here's 2 that are. I think what I'll do is go to a clean slide, because I don't think we'll have room to do it, and it might just make it. Okay. Here we'll have A is equal to 1, 2, 1, 1, and B is equal to -2, 4, 2, -2.
Okay. Well, first thing I want to do is pull out a 2 for that.
That's exactly what I was really wanting to do myself, okay? So this could also be written as 2 times -1, 2, 1, -1.
Oh, that looks familiar.
Yeah. Okay? Now, if you multiply a constant times the product, you can pull the constant out. So AB would then be 2 times, and can we multiply those as they sit? Okay, this one is about first and the third. It's going to be a 2 by 2.
Right, so go by the order we've been going through.
Right.
That'd be -1
Right.
plus 2, which is 1.
1.
Then you got -1 plus 1, which is 0.
Oh, which one? This one. Okay. Yeah.
Alright, and then, well, you already know where this is going.
Yeah, right.
And then 1, right?
Yeah, a 0 and a 1. And that is a clear indication, though we haven't gotten there yet, that these two matrices are inverse of each other. Otherwise, it wouldn't be. But if we hadn't pulled out the 2, it would have been a 2, 0, 0, 2, which is, yeah, still, okay. And let's do BA. So let's rewrite A. 1, 2, 1, 1. Okay, so BA is equal, we'll pull out the 2, and then what do we have here?
So 2 times matrix -1 plus 2, which is 1. And that would be 0. And up to the right of that would be 0. 1 below that would be, I don't know if you're ready for this, probably 0. Or no, 1.
Okay, okay. In fact, when you said 1 below that, and I thought you meant 1 below that, I wrote it down and thought, oh, no, that's not what he meant, so don't look, don't look. Okay, yeah, but it is 1.
I knew what it was going to be. I just kind of wanted to look at it, make sure,
Right.
verify.
Okay, good deal. And that is a special case. Now, another important quality of matrix algebra is that it does not have Well, not that I know of. The derivative of a system of equations, I'm not even sure I know what that means. I mean, yeah. Another important quality of matrix is that it does not have a general cancellation property for matrix multiplication. So if we know that AC happens to be equal to, let me get it the right way, BC, can we conclude from that that A is equal to B?
They're inverse. Right?
Huh?
They're inverse. They're not the same.
I don't even think we can say they're inverses of each other. That's the point. It's not doing, and that's what the next example it says is not necessarily true. Example 5 will demonstrate this. In the next section, you will see for some specific types of matrices, cancellation is valid, and that's when they are inverses. Yeah. Okay. But in this case, no. So let's do same thing with example 5. We're just doing, sometimes I think it's just as easy to do this. Okay, that's not bad to do. Okay. Here's A, sticking with fairly simple 2x2s, 1, 3, 0, 1, B being 2, 4, 2, 3, C being 1, negative 2, negative 1, 2. Okay. So we're first going to do AC. Whoops.
And negative 2 plus 6 is 4. And then 0 plus 2 is
2, you said?
2.
Okay. And then let's do, okay, wait, let's see. Yeah, BC. A little bit easier because they're closer to each other.
Minus 4, which would be negative 2.
Got it?
You got 2 minus 3, which is negative 1. And you got negative 4 plus 8, which is 4. And you got negative 4 plus 6, which is 2.
2. Is that what you said? Okay, I couldn't hear. Okay. And guess what? Those are equal. AC is equal to BC. These are indeed equal. Whoops. Okay. I drew that line, and then as soon as I quit drawing, it went crooked. You know, I drew it straight, and it did that. I think I hit a button or something. Okay. So those are equal, but A and B are nowhere close to being equal. Okay. Even though AC and BC are exactly the same. And I don't even think they are inverses of each other. In fact, I'm certain they're not. Okay, so it just...
So there's something connected between A and C and B and C then.
And that's it. And it has nothing to do with A and B. It just happens to be they do
by
that.
Anything else, it wouldn't have
You can't
C
always...
is a special one here.
I guess. Okay. So, you will now look at a special type, as if we haven't already looked ahead to this, square matrix has 1 on the main diagonal and zeros elsewhere. That's called the identity matrix. Two things about identity matrix. One, we just said, they're ones on the diagonals and zeros everywhere else. And the other thing that's implicit in that, they're always square. So this isn't just your reduced row echelon form, because you could skip a column there, and do other weird things. This one has to have ones on the diagonals, and to have a diagonal, it implies it has to be square. So these are square matrices, so you don't have to say M by N. All you have to say is N by N, or just sub N. I sub N is the N by N identity matrix where all your diagonal and sorry, I can't talk, are ones and zeros everywhere else. Okay, so give me what I sub 1 is. 1. Okay, not much of a matrix there. I sub 2 would be
1, 0, 0, 1.
Okay, and I sub 3.
1.
Well, okay, it's going to wake up sometime here. 1.
0, 0, 0, 1, 0, 0, 0, 1. I feel like a computer.
I know, that's what you sound like. Okay, all right. So there's your identity matrix. Now, as stated in Theorem 2.4, that was a little bit earlier. Oh, wait, no, not later, next page. The identity matrix, I sub n, identity matrix for matrix multiplication, it is called the identity matrix of order n. Okay, and that's coming up later. So you've got your book. So for those who don't have the book, yuck, I forgot that. I can't do that. Oops. Just sort of jot down what it says here. Properties of the identity matrix. Number 1, if A is a matrix, size M by N, not necessarily square, okay, then the following are true. First, A times an I matrix is equal to A. You need to tell me what size that I matrix has to be.
M.
I sub M. Okay, no, what did you say?
N.
N, yeah, okay, I was going to say. Has to be N because this is an M by N, so this has to be an N by N, so this comes out being an M by N as well. But it's not just any old M by N, it's identically the same matrix as you have. Okay? But then also this is true. Number 2 is that I times A is A. Is that the same I? No. This would have to be M, because then you would have an M by M times an M by N would give you an M by
Gotta have the same N
N.
terms there.
And not only would it be any old M by N, it's identically the same. So even though we say, you'll almost, it seems like I've seen it, and maybe not in this text, but in others, AI is equal to IA is equal to A, you know. The only time you can say that is when A is a square matrix and then I is the same identity matrix. So yeah, you can say it that if A is squared, then that would be a legal statement. You don't have to use the subscripts. Okay. And that's what they say in the remark in the upper left. Note that if A is a square matrix of order n, then AIN is equal to INA, which is equal to A. So then you can say it. All right, so what we're going to do now is multiply, and validate that for at least a couple of matrices. Here's the first one. 3, -2, 4, 0, -1, 1. If we're going to multiply that by identity matrix, which one had that better be?
This is a 3 by 2.
Mm-hmm.
So we need a 2 by 2.
Yes, so that would be
1, 0,
1, 0, 0, 1. Okay, let's see if we can do that multiplication. What size will this be?
be a 3 by 2.
It's got to be a 3 by 2 because it's trying to replicate itself, so it better be that size. And where do you want to begin? Upper left. Okay.
That would be 3.
3.
And below that would be 4.
4.
Below that would be -1.
-1.
And then
Yuck. Wait. Okay. Got it back. Okay.
that'd be -2, 0.
Yep, it does replicate itself exactly. Okay.
I wonder why.
Identity matrix. All right. Now, if we had another, we're going to have this being a column matrix, -2, 1, 4. It's really slow. And I'm going to multiply identity matrix over here. What size would this better be?
3 by 3.
Got to be a 3 by 3, and what would that be then?
1, 0, 0, 0, 1, 0, 0, 0.
Okay. And let's see what we should get.
Hold on, I'll put it in the wrong order. Alright, so yeah. 2.
So -2.
2. 1.
Right? 4. Yep. Sure enough, you get it if you can keep your slide on. Okay.
Gotta multiply by 0 a lot, so hope you're
What's that?
comfortable with multiplying by 0.
Right. Okay. They don't give us too many practice ones to do with that. Okay.
Gotta know those 0 multiplication tables.
Yes. Now, it seems like there should be a break in the page or something. But right below this, it goes in, and I guess that little blue box over there on the right indicates you do have a break in the page, but it almost reads like this follows from that. It doesn't. This is a new subject. So what I'll do here is this. I thought I would do that. There we go. All right. For repeated multiplication of square and only square matrices, because you just can't do repeated multiplication of any other things unless they're square, we use the same exponential notation as used with real numbers. So a to the first power is still just a. Remember, a is a square matrix. Huh?
Even this just
First power is itself. Right. Okay. And a squared is simply a times a. And we usually don't even use the dot, any kind of a thing, just write it AA. Okay. And a cubed would then be a times a times a. Okay. Got it. Yeah. So that for any positive integer k, a sub k, a to the kth would be a times a times a. I'm putting the dots in there now. And you would just have k factors. Okay. Multiply them all out there. Okay. Now, It's convenient to also do this, a to the 0th. And what in the world do you think that would be?
Identity matrix.
And of size n, whatever size a was. Okay, a is a square matrix of order n. Now, those definitions allow you to establish some other properties, and here's one. If you have a raised to the jth power times a to the kth power, where a to the j is j factors of a and a to the k is k factors of a, then what would this product be?
A to the
J plus k. Add them. Yeah, if you had j's here, j of those, multiply that by k of those, then you would have
You just add the exponent.
add the exponent, exactly, just like you do with powers of numbers. Okay, so that works. And then this one, a to the jth raised to the kth, that would be your
Oh, sorry, that would be JK.
jk. Okay.
Just kidding.
Yes, or John Kennedy, or whatever, okay. So that'd be a to the j times a to the j times a to the j. You would have j in each one of those, and if you had k of them, j times k. Yeah. So that. Okay. So that's pretty much like you would expect. So we're going to do a few of those, and they're not lots of fun, though they're not bad. So let's do a cubed, where a is, do we have room here? I think we do, is,
You can erase it if you want.
okay,
Just so we'll have enough room for sure. That way you don't have to do a whole lot of scrubbing later on.
right. So a equal a simple 2 by 2, 2, negative 1, 3, 0. Okay, and we want to calculate a cubed, which would be a times a times a, which would be 2, negative 1, 3, 0, times 2, negative 1, 3, 0, times 2, negative 1, 3, 0. Okay, and remember, it doesn't matter what order you do, any order will work. It's associative. Yeah, do 2 at a time, exactly.
So, first one would be 2 minus 3, which is 1.
Got it?
Or negative.
Yeah, negative 1. No, it's not. Positive 1. Isn't it?
Oh, it's 4. Excuse me. Yeah, it's
Yeah.
positive 1. Hadn't read the first time. Should have just.
Right. Goodness gracious. Nope.
It's 6. plus
Wait,
0.
I got to get my pen back. It's being weird. Okay.
6 below that?
Yeah.
Or no, 9. No, it's 6. It's 6. Sorry.
Yeah.
Yeah, said it right the first time.
Okay.
Right, then negative 2. And then negative 3.
Well, I didn't hear the last.
Negative 3.
Negative 3. Okay. Then multiply that by 2 minus 1, 3, 0. And you get
2 by 2 matrix. That would be 2 minus 6, which would be 4, negative 4.
negative 4.
And then 12 minus 9, which is 3. Yeah, 3. And then negative 1. And then negative 6.
What was the last you said?
Negative 6.
Yeah, okay. All right. That's what we get.
I like it when there's zeros.
It sure is nice, isn't it? When we do determinants, it's really nice. Okay. Now,
Actually, one of the Scholars Bowl tournaments we went to, the one at UAB, I learned how to do determinants there.
Mm.
Because there was a question about it, and I was like, love matrices. Why can't I don't know what to do. And then she kind of told us about it, and I was like, oh.
Yeah. Now, even though these are not hard to do, the definition is pretty simple. There's nothing you can conclude at the end. This a cubed has no relation to that except it's a times a times a. You can't look at that and say, oh, that's a cubed, you know. Nothing is cubed, nothing is -1 is cubed, you know.
I find it interesting that the diagonal has stayed the same.
The
-1 and 3.
Yeah, and I think the reason for that is that 0 down there. I would be surprised if that's not the culprit that makes that happen. I haven't proved that or anything, but that's just my gut feeling on it. Okay. So, it's just what they are. There's no simple way to do it. You just have to multiply. Now, back in section 1.1, you saw that a system of linear equations must have exactly one solution, or infinitely many solutions, or no solutions, one of the three. You can use matrix algebra to prove this, and that's what theorem 2.5 does for us. I guess I'll write it down since. Okay. For a system of linear equations, precisely one of the following is true. Well, this is the same thing we just said. The system has exactly one solution, has infinitely many solutions, or no solutions. Okay? And then they go into a proof of it. And since you are now a math major, it's probably not a bad idea to think through this proof. Okay?
The one before transpose of the matrix. Oh, no, I see.
Yeah, bottom of the page, yeah. Bottom of page 56. Yeah, it's pretty straightforward, and I think they describe it and explain it well enough. Now, there's a little discovery at the top of page 57, and usually these are going to lead you into something that's coming up soon, okay? In fact, sort of right away, okay? But before we can do that, we'd have to have the definition. So let's do the other part first. The transpose of a matrix is formed by writing its column as rows. Therefore, its rows will become the columns, okay? So if A is an M by N matrix, okay, and it would be A11, A12, A13, dot, 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 A1, M, A21, A22, A23, dot, 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 A2, M, A31, A32, A33, dot, 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 up to A3M, dot, 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 down to AN1, AN2, dot, 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 AN3, dot, 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 okay, never mind, A sub N, M. Okay.
You got the, supposed to be ends on this axis?
What's that?
Is it supposed to be, you got the ends and the ends mixed up?
Okay. Oh yeah, you are right. I was doing N by M, and I had forgotten I wrote the other. So this is the M, 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 M. Whoops. How did I have that? Okay. Hit the wrong button here. Okay. And this would be N. That's an M and that's an N. Okay. Yeah. Sorry about that. A sub M. M by N. Okay.
So we
Now.
just got to take this thing.
Right.
This would.
Well, not quite, but close. its I can't talk. The transpose AT then would be,
Oh, it would flip the row over.
yeah,
So you got it like.
yeah, yeah. Basically, you almost have the right idea there. Reflect across the diagonal, basically, is what you're doing. This will now be A11, A12, A13, dot, dot. Say 1-3 and write 3-3. Kind of weird.
You're just ready to be done writing this.
You got that right. Okay. Down to A1. N it is. Okay. I couldn't remember which I had. Yeah. Okay. A21, A231, dot, 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 out to AM1, A22, A32, dot. They show up and they disappear. Okay. AM2. Okay. A 2, 3, A 3, 3, dot, 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 A M3, dot, 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 A sub 2 N, dot, 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 A sub 3 N, dot, 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 A sub M N.
It should be NM, right? No, you're right. You're right.
Yeah. Yeah.
I'm trying to flip the order, but you're not supposed to.
Yeah. Well, no. You flip those, but diagonals stay the same. Yeah. They won't go. Though it's not exactly a diagonal because that doesn't have to be the same. But
So yeah, you just flip it
Okay.
over diagonally.
M, right. Okay.
Let's do an example so we can see
All
what
right.
the heck's going on.
But that's what a transpose means. So let's go up and do the discovery first, and then we'll come down and do the example. Okay? So let's clear these. Hopefully we don't need that anymore. Here's A. 1, 2, 3, 4. Okay? Here's B. 3, 5, 1, negative 1.
Let's see. Hope it's not like 5, 6, 7, 8.
What's that?
I was
Yeah.
half expecting it to be 5, 6, 7, 8.
Yeah, that would be a little, okay. First thing we're going to do is AB. What is AB? Can we do that fairly straightforwardly?
That would be 3, 5.
Got it?
And then 9 plus 4, which is 13.
Got it?
And you got 5 minus 2, which is 3. And 15 minus 4, which is 11.
11 you said? Okay. Now, let's do AB transpose.
That would be 5, 13, wait.
3, 11, right?
11,
Okay?
I was making sure I was calling it out in an order that made sense since I usually do columns.
Okay. Now let's do A transpose.
That would be 1, 3, 2, 4.
Got it?
B transpose.
B transpose.
3, 1, 5, negative 1.
Okay.
I have a
And
feeling
let's
it's
do-
like hairier with the matrices.
What's that?
I feel like it's going to be hairier as the matrices get bigger.
Oh, you better believe it. Okay. What's A transpose B transpose? Okay. Yeah.
Then 6 plus 20, which is 26.
26. Okay.
And then you get 1 minus 3, which is -2. And 2 minus 4, which is -2.
Okay.
Um,
Almost makes it look like we haven't done something right, doesn't it?
I think the 2 is the -2 of the 26 swapped.
What's that?
I have the 26 as the top right.
Oh, you did. Okay, I'm sorry. I thought you were doing your normal.
No, column.
Right. But okay. I thought you were doing your normal way. Okay. Okay.
Maybe I messed up and did it the normal way.
Okay.
Check now. So 3 times 3. 9 plus 15 is 18. Then 1. Yeah. Minus 3, which is -2. That's what.
Okay. All right. And guess what? That doesn't look anywhere close to anything related to nothing. Okay. So let's try one more iteration. Let's try B transpose A transpose. Now this is going to be tough because I don't have room to write it out on the edge. So let's just do 3, 1, 5, -1 times 1, 3, 2, 4. This is B transpose A transpose.
Okay, so top left.
Okay.
That would be 3 plus 2, which is 5. You go down a row, weird way, yeah,
Mm-hmm.
backwards. 5 minus 2, which is 3. Then next row, next column, I should say. 9 plus 4, which is 13. And then bottom last 15 minus 4, which is 11.
15 minus 4 is
11.
11. Okay, I couldn't hear what you said. Okay,
That looks
and this is, the way it happens to turn out then, is AB transpose is equal to B transpose A transpose. So,
Is that always true? Or just
yes, that is a generalization. Okay, as long as there's square matrices of the same size. Okay, and in fact, I want to say as long as the multiplication makes sense, so they wouldn't even have to be squared. So if A was a 2 by 2 and B was a 2 by 3, then this would be a 2 by 3 by 2. No. This would be a 3 by 2, but yeah, I think you would do it. It would work. They don't even have to be squared. It just have to be sizes that you can multiply to begin with. And if they are, that'll work. Okay. So sure enough, that's the rule. Let's do example 8, which is
So,
more of the same.
A transpose times B transpose equal BA transpose?
Yeah. Same type fail, right? All right. So let's do, jumping back to simpler stuff, is here is A is 2, 8, a column matrix or column vector. What is its transpose?
BA2?
No, you don't reverse.
Oh.
The
See, we've only
column
been
becomes a
working
row.
with square matrix.
Huh?
We've only been working with
Square matrix, right, yeah.
And that's
So that would just be 2, 8 also, but now written as a row matrix, okay? Now you wanted a square, you get a square. B is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. What would be its transpose?
Alright, so it'd be
Uh-huh.
4,
Yep.
7,
Right.
2, 5, 8,
Got it.
3, 6, 9.
Perfect. Okay.
Good.
Let's do C. That means yes in French, in Spanish. Okay.
In French.
We. No. Us. No. 1, 2, 0. 2, 1, 0. 0, 0, 1. That would be.
With this, what I want to do, instead of doing it like row at a time or whatever, is go ahead and write our diagonal down.
Right.
So you write it 1, 1, 1,
Mm-hmm.
and then go from there.
Yeah.
That's what I want to do.
Okay, and you certainly do. Here's what I want to do. I want to write it just like I called it out before, but writing vertically now. 1, 2, 0, 2, 1, 0, 0, 0, 1. Okay, that's how I do it. But I wouldn't do it just audibly because no one will know where I'm putting the things. Okay, so that's how I do it. To me, that's the easiest way to write it.
Just read it off.
Read it off and write in college. Yeah.
Yeah, like I do it half the time.
Yes, exactly. You should do really well with these. Okay. Let's see if we can get D up at the top. Okay, here's D. It's a 0, 1, 2, 4, 1, minus 1.
0, 1, 2, 4, 1,
D transpose then would be,
0. Below that.
huh?
Below that.
Below that,
1,
1,
2, 4,
2, 4,
1, negative
1, negative 1.
I like
Got
this
it.
better.
I like it too. It's so easy to do that way. You could have also written the rows as columns. I mean, the columns as rows. That works the same. That's it. Okay, and I think the book got it right too. Good for them. Okay. Now, note that the square matrix in part C, that's this one.
It's the exact same.
Yes, and the reason for that, sort of going back to what you did, notice what your diagonal is.
It's all ones.
All ones. And that was all ones. Because your diagonal doesn't change in...
And if you flip over what you have left over, it's all the same on both sides anyway.
Right. And this kind of matrix like this is not always if it's all ones. It doesn't have to be.
Could be
I
all
think
twos.
it just about always is. But the thing is, you must also have the other parts corresponding. This is called the diagonal matrix. It reflects across the diagonal.
Just whatever you have in the top or the bottom, is, if it's the same, it's going to have the same.
Yes, and then when you flip them, they're going to be the same too. Exactly. Okay. But they don't have to all be ones. Okay. Oh, I'm sorry. It is a diagonal matrix, but it's also a symmetric matrix.
That's
That
right.
a square matrix in part C is equal to its transpose. If the square matrix is equal to its transpose, such a matrix is called symmetric. Matrix is symmetric when A is equal to A transpose. That's what it means. From that definition, it should be clear that the symmetric matrix must also be square. It's got to be square, and that Aij is the same, and Aij is equal to Aji for every one of your i's, as long as the i's and j's are not the same. Okay. If they're the same, they're the same. All right, so let's look at some properties of transposes. How are we doing on time?
It is 10 till 12.
Oh, good
Yeah,
deal.
25 minutes.
Yeah, moving nicely. Okay,
You're
here's
getting a lot done.
theorem 2.6.
Okay.
Okay, A and B are matrices with sizes such that you can do it. Okay, C's a scalar. So A, B matrices. I'll put properly sized.
So square matrices work with.
They don't have to be square, but if they're not square, they have to be dimensions so you can do the multiplications, okay, or whatever they're calling you to do. C is a scalar, okay? Then these are true. Now, first one, hopefully, is really obvious. If you start with the matrix A, transpose it, and then transpose the transpose of A, you better get A again. And that's not just for squares, it's for any size matrix. Doesn't matter what size A is. Huh?
That makes me think of like negative A multiplying it by negative 1.
Right, exactly. You get back to A. All right. The second, okay, this one may not be quite as obvious, but hopefully it's not too bad. A plus B transposed is going to be A transpose plus B transpose.
Distribute the T.
Huh?
Just distribute the T.
Yeah, as the exponent, right? No. Yeah, okay.
I didn't say that.
Okay, good.
Multiplying the D. That's not,
All right.
That's not what I think.
But that isn't an exponent, it's a operator. And in this case, that is good to do. Now, here's this one. This one may come as a little bit of a surprise unless you... No, it shouldn't. Okay. CA transposed is the same as C times A transpose.
It's just like, alright, so you either you flip it then multiply, or multiply then flip it. It's the same numbers.
Right, exactly, because what this means, every element in A is multiplied by C. So when you flip them, they're still going to be multiplied by C because it's in every element. So you can pull that out and transfer. Yeah, exactly. The product of a flip is the flip of the product. That no, that's not right, is it? Okay.
He's creating new laws.
Yes. And number 4. Okay. And this is the one we just did. AB transpose is, what was that? B transpose times A transpose. Now, of course, the sizes must be so you can do that. And what that restricts you to, certainly square matrices are fine, but even though you could have A being an M by N and B being an N by P, and this would work,
It has to be M by N and M by M.
Exactly. Before the innards must be the same, now the outers must be because you're...
They have to be the same size matrix.
Yeah.
Not necessarily square, but like 2 by 3.
Wait a minute, let me back off and say. Let's just say, give me a number.
2 by 3.
2 by 3.
That has to be a 3.
3 by something.
Something.
And what would you want it to be?
Probably 2.
Okay, but let's try something else. 4. So let's do that. See if it'll work. This is what, 2 by 3 you said? Or 3? Huh?
2 by 3.
2 by 3. This one would have to be a 3 by something, and we're going to try 4 rather than the other. Okay? Now, the product then would be a 2 by 4, and its transpose would be a 4 by 2. Right? All right. Now, let's see this. The B transpose would have to be a 4 by 3, right? And
Would be a 3 by 2.
3 by 2, right? And then you could multiply that together and get a 4 by 2.
Okay, so just the innards have to be the same.
Yeah, exactly. It just have to be, you can do that first one. And if you can do the first one, then you can do it one. Okay. All right.
Because of the transpose.
Okay. And they have a little proof there, and we've really almost talked our way through the proof. But
I think I have a good understanding of how it works.
Right. They used I's and J's rather than 2's and 3's and 4's, you know. So, all right. Little remark here. Remember, if you reverse the order of the multiplication when forming the transpose of a product, okay, and we just proved that before, so yeah, we got that down. Now, properties 2 and 4 can be generalized, 2 and 4 here, can be generalized to cover sums or products of any finite number of matrices. So this could be, 2 would then be A plus B plus C transpose would be A transpose plus B transpose plus C transpose.
The product is kind of
Yeah.
interesting.
Now, and then the fourth one, if you had a triple A, B, C transpose, then that would be C transpose times B transpose times A transpose.
That is if they were all the size they needed to be.
As long as they will work here. Pick this L by N, this just has to be an N by P, this one has to be a P by Q. Whatever you want to use there. Then this would be a Q by P, this would be a P by N, yeah. So that would work, no matter what the site. So as long as they work in the first one, they'll work the other way.
Flip the matrices, you flip the order of the multiple.
I'm getting hiccups, sorry.
That was early.
Okay, let's try example 9. It's a bigger one, but it's doing the same thing as the little one did before. Sorry. Here's A. 2, 1, negative 2. Negative 1, 0, 3. 0, negative 2, 1. Okay, that's A. Here's B. B. Sorry. 3, 1. 2, negative 1. And 3, 0. Okay.
Alright, so
And what it needs to show is AB
we
transpose.
can either take the transpose of both and then multiply B times A, or we can multiply them and then take the transpose of A.
So they start with the first, what you said second, they do first. So let's do AB first. What would that be?
So that's going to give us a 3 by 3, right?
Yeah.
Alright, so 6.
What size will your answer be?
Oh, it'd be a 3 by 3.
Will it?
Oh no, it'd be a 3 by 2.
Yeah. Okay. That's what I wanted to bring. Okay.
So it'd be 3 times 2 is 6.
Okay.
Plus 2 is just 8. Minus 6, which is 2.
Okay, what you get at the end?
2.
2. Okay. Yeah. Sorry.
Next row down,
Okay.
negative 3 plus 9, which is 6.
Got it.
Row below that would be 0, negative 4 plus 3 would be negative 1.
Got it.
Alright, starting at the top of the next row.
Okay.
2 minus 1, which is 1, is 1.
Okay.
Next one below that would be 1, negative 1, and that's it.
Yep.
1, 0, 2, 2.
2. All right. Now let's transpose that. Yep.
So this is going to be 2 by 3.
Yep. Let's transpose that. Is that what you were doing?
2, 1.
Oh, okay. All right. Yep.
6, negative
Going down?
Yeah.
Okay.
6, negative 1, negative 1, 2.
Okay.
I feel like that's sort of cheating.
What's that?
I feel like that's sort of cheating.
Yeah, it sure does, doesn't it? Okay.
You can go get some water.
I think I can last it out, but let's just see. All right, sorry. Trying to figure out. Let's write it here. B transpose is.
Okay, that's going to be another 2 by 3, and that would be 3 and 1 below it, 2, -1 below it, and 3 and 0 below it.
Okay. And A transpose.
And that would be a 3 by 3 still.
So again.
3 by 3 as well.
Right.
And so it would be 2, 1 below that, -2 below that, -1, 0, 3, 0, -2, -2.
It's just my pen is slow. I'm writing, but it's not. Okay, so now we want to do B transpose times A transpose. Yep.
B2 times A2.
Yep.
We should get 2 by 3 out of this, right? Or no?
Yep.
Yeah, okay.
Yep.
So that'd be 6 plus 2, which is 8, minus 6 is 2, right?
Yep. Okay.
Below that would be 2 minus 1, which is 1.
1.
Next column here be -3 plus 3, which is 0. No. Wait.
Yep.
-1
Yep.
plus 0. No, -3
Yeah.
plus 0 plus 9.
Right.
So it'd be 6.
6. Right.
Getting confused because I have them written above
Right.
each other instead of beside each other.
Right.
And then
Yep.
below that would be -1. Alright.
Right.
And then the next row or column would be 0, -4 plus 3 would be -1. And 0, 2 would be 2. So exactly the same thing.
Absolutely. And we did show, indeed, they are the same. So that's example 9, and they truly are the same. Do we have time for 10?
Yeah, we have like 10 minutes.
10 minutes, excellent. I thought we did, but I just can't believe how fast we're flying, okay? Okay, example 10. What happens if you multiply a matrix by its transpose? Let's try 1.
That's frightening.
What's that?
I said that's frightening.
Yes. Here's A, 1, 3, 0, -2, and -2, -1. What would be its transpose?
It would be 1 and 3 below it, 0 with a -2 below it, and -2 with a -1 below it.
Got it. And let's multiply those. Oh. Ah.
And this
Wait, I got to get my pen back.
2 by 3,
Yep.
3 by 2. No, I go back. Yeah, 3 by 2 and 2 by 3.
Second.
That would be a 2 by 3 and a 3 by 2, right?
Right. And what size will it wind up being?
Be a 2 by 2.
Okay. Now, we do it A times A transpose.
Right.
A is a what?
Is it
Yep.
3 by 2 or
3 by 2.
It is a 3 by 2, okay. And it's a 3 by 3.
3 by 3. Okay.
I had it as
Yep.
backwards.
Okay.
Alright, now. So you end up with 3 by 3. Alright, we get, let's see.
What's that?
Yeah.
Okay.
Be, 1 plus 9, which is 10.
10.
Row
Go.
below that and be 0 minus 6, so negative 6. Row below that be negative 2 minus 3, which is negative 5.
Okay.
And you get negative 6 again.
Okay, wait. Yeah. I'm just in the middle of a hiccup and I lost where I was. Okay. Yeah, okay, yeah.
On the right,
Yeah.
first row. So it'd be negative 6.
Sorry. Goodness gracious. This is getting to me. Okay, we're the 2, 1. Okay.
Negative 6.
Yeah. Oh, sorry. Wait a minute.
Positive.
I might have to go get water because I can't hold my hand still
Okay.
enough when I hiccup. Let me see. 1, 2. Okay. Is that where? Okay. That would be a minus 6. Okay, got it.
And then below that's a 4.
Okay. Yeah. And below that is a
2.
2. Okay.
And you get negative 5.
Yep.
And then 2.
Yep.
And then a 5.
Yep. All right. Now, I don't know if anything reaches out and grabs you about this right at the beginning.
Yeah. And
What?
it's a symmetrical matrix.
It is a symmetric matrix. Notice the diagonal doesn't have to be 1 like the last one was, but the opposite things are exactly
Negative 6,
exactly the
negative 6,
same.
negative 5, and 2 and 2.
This reflects across the diagonal. Exactly. Now, the interesting thing is, let's do it the other way.
So AT times A.
Yeah, let's try that. What you reckon this is going to be?
That's going to be a 2 by 2.
This will be your 2 by 2. Okay.
Alright, so that would give us okay, I wrote it down right. Okay. I was making sure I wrote it down right.
Okay.
That would be 10,
Okay.
right?
Okay. Sorry. What did you say it was?
10. 1 times 1 plus 9.
Okay.
You want to do it back?
Okay. I'm trying to see where you're doing. You're doing first row, 1, 0, negative 2
Oh,
by
yeah.
first column.
I got it.
You
Okay, I got it now.
the other way, yeah.
Flipping them around and
Right.
flipping them and stuff makes it weird, right? So 1,
Yep.
0, 4, so that'd be 5.
5. Okay.
Okay, and then below that be 3 minus 3, which is 0.
Okay. Let me see. 3.
Oh wait. 3 minus.
Yep.
No, it'd be plus 2, which is 5.
Yeah. Okay.
Alright, next row. Be 3 plus 0 plus 2, which is 5. I'll tell you the last one's going to be 5. 9.
Don't think so.
4, which is 13, plus 1, which is 14.
Okay. I can't write. 14.
5, 5, 5, 14.
Okay. But what is this also? A symmetric matrix. Here's your diagonal. These are opposites. Okay. So it
It's
is
just
still
coincidence we have so many 5s.
Yeah. Yeah. Basically. Now, all that they were going to say. They were going back to this, that this one, because this is A times A transpose, well, that's the same as, A transpose transpose times A transpose, right? A times B would be B transpose times A transpose. So it's A times A transpose would be A transpose transpose, which is A times A transpose, which is A times A transpose is equal to A times A transpose, symmetric matrix. Yeah.
You lost me, but I believe you.
Okay. Remember, the definition of a symmetric matrix is that A goodness gracious. I'm just going to read it from the book, so because I don't think I can say it without it. Okay. Goodness gracious, this is choking me.
It's like a hiccup attack.
Yeah, there was actually a president of the University of Nebraska system. It's University of Nebraska at Lincoln, University of Nebraska, Omaha, University of Nebraska Medical Center. He had a case of hiccups that went years. Sleep all the time. He hiccuped nonstop. That's what I heard anyway. And I just can't imagine that because they're awful when they happen.
Well, it's just your diaphragm getting out of sync with everything.
Yeah.
Isn't it? So
Yeah.
it's trying to contract when it's not supposed to.
Yeah. Now,
Forcing you out.
Now, what this said was that for a matrix to be symmetric, if matrix A is symmetric, it's equal to its transpose.
Okay.
Okay.
Yeah. All right.
Okay. Now, here's a matrix. A transpose is a matrix. Okay? So A times A transpose is a matrix.
That one right there.
Right, okay. Now, the transpose of this matrix
Is A transpose A.
is going to be A transpose transpose, the second one, times the first one transpose. But A transpose transpose is A, and this is A transpose. So
It's the same thing.
yeah, its transpose is the same as what it started with, so therefore it's got to be a symmetric matrix, and the same thing there too. Go. Okay, easy enough for you to say.
And we are out of time.
And we are out of time. But we do have time to do just a couple things. There's a linear algebra applied here, which I think is talking about search algorithms. And
Like Rubik's Cube solving.
yeah, basically. And basically, you're dealing with transposes of things. Evidently, Google has a very special one that I believe is still a big secret. You know, they're the only ones that, yeah, that's how Google made its name, was their search engine. That was originally what a Google was. Then the company grew and grew and grew and actually has split since then, but yeah, never mind. Okay, homework exercises in 2.2, any of the odds 1 through 5.
I think this is the one that has all of them.
Yeah, yeah, this one does. 7 through 11, do 13. Odds 15 through 19, do 21, do 23, do 25, do 27. odds 29 to 33, do 35, do 37, either 39 or 41, either 43 or 45. Think through the true false, 47, 49, do 51. This is the power of a matrix. You're raising it to the 19th power. Have lots of paper handy. No, I think you'll find it easier than that. Do 53, do 55, and then on some of the proofs or guided proofs, any of the odds 57 through, 65 that you choose to. And then they're dealing with symmetric matrices, but they then define in the exercises, which aggravates me, what a skew symmetric matrix is. So try to do 67 or 69. Then you got another couple proofs, 71 or 73. And then if you choose, 75. And we'll begin next time with 2.3. Good deal. Got a lot done today.
Next section.
So let me stop this.